Thanks very much, Edouard. And I'm also very happy to be here and very honored to be here. And the work I present, this is not single work. This is done in an interdisciplinary framework and also international framework. So I want to acknowledge some people from our group, but also the Pages 2K group. Johan is here, Jan is here, and also members from integrated projects we are currently running together with the climatic research units in Norwich and from Langshu University in China. So I will give some insight in climate change related to temperature, but also to hydroclimates in Asia, and I'm very happy that the speakers before gave an excellent introduction in proxies, in the fields, in monsoon, and interaction with society. So there's some things that you will hear again. So the outline on the top, this is the castle we are working on in Giessen. So that's a 500-year-old castle where the Department of Geography, so we have also nice buildings there. But the main topic is, after a short introduction, I will shortly show you the concept of climate reconstructions. We all deal with proxies, we all deal with methods, and I want to show, just for some people that might be not so familiar, the schematic topic behind any kind of reconstruction on a high resolution. And then some recent development and improvement of proxy network to reconstruct past climate on different time and space scales. Edouard already introduced them in terms of Pages 2K. That's an important step, and I will give some more insight in this. Then I want to show some examples from local reconstructions to continental temperature reconstructions over the past centuries to 2 millennia. And I will give you some insights across Eastern Asia that we just did some time ago together in a joint framework. And then the second part will be related to hydrological changes, hydrological evidence from East Asia. And I will give you some examples about the challenges, opportunities, uncertainties, but also preliminary results. Gerard already did a very good job in introducing proxies in the long term and also the uncertainties underlying and what kind of dynamics is behind these monsoon dynamics. At the end, some conclusions. So I want to start with a global view of instrumental temperature trends. This is the last 120 years approximately from the Giessen NASA. From 1881 to 2017, the temperature change during summertime. As you can see, more or less the whole globe is warming. We have some gray areas. This means we don't have too much data or not enough data that can resolve a long-term trend. So we have a lot of areas that have missing data in the long term. And if we have a look just here in this part of Eastern Asia, so it's not easy to get really long-term measurements to derive a significant trend over the area. We have many areas that are gray, so we don't have really long instrumental data. This is the distribution of temperature data for the period 1900 to 1930. And as you can see, there's a huge gap also here in Asia. And through time, mainly from the 1950s with the development of the World Meteorological Organization, there was also then an increase of instrumental data for China. But I want to make sure that it's clear from this plot here, if we were to talk about instrumental data the last 120 years, there are many areas that have really big gaps in terms of instruments. Then if we have a look at the last 30 years from 1988 to 2017, it gets much better. Still areas, they are gray, especially here in the Antarctic, but also in South America and Africa, but still parts of Asia do not have really significant amount of temperature information or observational evidence. If we average this area here, just to get a spatial average and the change of temperature over the last about 100 years, we see that from the 1920 to today, we have more or less stable summer climate, of course with a minor amount of temperature series, but actually from the 1960s, we see this strong temperature increase. This is a plot of the last IPCC report where they show continental temperature development over the instrumental periods, here over the last 150 years for the majority of the areas, and then also what the models tell us, the forced, the unforced, just to see to what extent can we explain current temperature changes in terms of forcing. And if we have Asia here, we see, you might not see the details, but nevertheless the strong temperature increase here over the last 50 years, and models just force with natural forcings cannot account for this warming. Nevertheless, that's not the point here I want to address about detection and attribution of temperature change over the recent decade. What I would like to especially emphasize here, if we go further back in time, what kind of evidence do we have? Can we really say something before the 19th century? What information do we have? What is the variability behind? What are the uncertainties behind it? So for this, what we heard already, we need proxy data. There's a collection of different proxy data. I will present a few of them. Gerald showed a couple of them, Jan already in terms of tree rings, and we heard also in the morning from other talks about documentary evidence from Elena, from you, Edouard, also from other proxies. So there's a variety of various proxies that can resolve parts of the temperature variability over time. Now, if we just have a look, how do we do any kind of reconstruction? This is a schematic view of how people usually do that. This might change a bit from proxy to proxy, but nevertheless, it's first the research on the proxy. So we go in the fields, it's a biological part. We select the places where we have proxy information, of course, but potentially they are also in places where it's climatically relevant and interesting. Then we take these samples, we go to the lab, we date them, we do some kind of pre-processing, what Jan showed very well in terms of tree ring research, and then comes statistics. We want to see in a calibration period to what extent this proxy is reflected in climate. And then we have a validation period where we try to see if this statistics we derived in the instrumental period holds also in an independent period. And if this is the case, we can apply these statistics to the long time series and actually can derive a temperature or precipitation or any kind of other series back in time. And this is something, an example from archaeology, where you go in the fields, you do the measurements, and finally you come up with a fancy curve that tells you something about past climate. With uncertainties, we heard also, we can just explain parts of the variability that's important, and that I will come back to this also a bit later. That is the distribution of proxies that have been presented in the last two IPCC reports, AR4 and AR5. You see the distribution of proxies the year 1000. So you see hardly any evidence here in the south. This is just high resolution, so it's monthly to yearly resolution data. You see a couple of tree rings in the northern hemisphere, but nevertheless, more or less everything is empty here in Asia. And then 1500, it looks much better, and 1715 also, but there are huge gaps in different areas of the globe. So this was one point, and also Mike Mann was working on this, on an improvement of networking. That's his network here, and this looks a bit better, what he was published 2008. So the main point is here, there is proxy data around, high resolution, spatial distribution, mainly related to the northern hemisphere, and there's not too much here in Asia, as reported here. Then there was the idea of PAGES initiative that Edouard was already mentioning, that took place from 2012 to 2017, where specific groups of researchers came together, and the major aim was to understand climates much better on a continental scale for the last 2000 years. So it was about compilation of data, it was interpretation of proxy information, and then to derive quantitative measures about temperature and precipitation changes over the last 2000 years in the ideal case for all the continents. So there were different targets, different aims, different approaches. One was the understanding of proxy data. So we want to understand what the data mean if we integrate them in a multi-proxy scheme. but also forward models, process-based understanding of proxies. So we want to take these information and then to come up with spatial reconstructions, spatial mean reconstruction or temperature and precipitation in space. That's a distribution here. I will come back to this as well. This is a spatial reconstructed temperature field, and this I will come back as well. The other point was the understanding of climate. For this, what we will hear more in the talks that follow mine will be about climate models. So we wanted to know what is behind the temperature precipitation changes in the past. What is the dynamics? What are the potential explanation for the changes? Is it solar driven? Is it volcanic driven? Land use changes? When does anthropogenic impact starts? What Edouard was already mentioning below. And then also some kind of methodological framework. What kind of methods do we have to reconstruct? What kind of methods do we apply to compare reconstructions with models? So these areas in the pages 2K network related to the different continents, I will present something here about Asia 2K, where I was involved. This is the network, so people realized, okay, there must be much more information around that was actually put in the pages chapter. So people in the different groups collected information, they compiled them, they interpreted them. There's a lot of expert knowledge, not only statistical knowledge, that brought all this network together. And you see from the different colors, they reflect different proxies. So you see in the US a lot of tree rings, but also here in Asia a lot of tree rings. But nevertheless, there are also some new evidence coming up in the Southern Hemisphere. And that's the change of proxies over time, over the last 2,000 years. And you see at the beginning just a few of them, and then from 1300s with a big step towards a lot of tree ring information that can be used for climate reconstruction. So if you take these proxy data for the specific continents and then you apply some statistical methods, you can come up with a spatial mean reconstruction for each continent. This was published 2013. There are the different continents. We saw this already in the morning. And what is red means that's time, so 0 to today. Red colors refer to warmer than the last about 200 or 300 years, and what is in blue is colder. So you see the change of temperature over time for the specific areas, but here you can also see is there some agreement across the continents and across time. And this was a very important contribution. This was a very important contribution also to be involved in pages 2K and also in the IPCC report. However, one problem is here that these reconstructions are based on different proxy data, different amount of proxy, as well as different statistical methods. So a second part of the pages 2K was then really to harmonize also, to take the same data, to apply the same methods, and to come up with some consistency in terms of statistical model. But here you see already there are some areas in Asia that seem to be rather warm during a medieval period, and then some colder periods, and at the end, as I showed you the last 60 to 70 years, strong temperature increase in summer temperature. You can go from the mean, from local or a continental mean to space to a globe. And this is like a spatial extrapolation of the proxies that were gathered during these pages 2K first version to show you the year after the Tambora. This is the spatial temperature map of 1816. So taking all the stations, using some fancy statistics, you can say something about the state of the globe. This seems quite a cool year. Many parts were blue. Nevertheless, I don't show you the uncertainties. The uncertainties are large. And this is an important issue. If you do some kind of paleo reconstruction, you can estimate something statistically or from any other parameter, but you have to be aware and sure and also show the uncertainties underlying. So the uncertainties here, I would estimate, would be plus minus 1 degree or even more in areas where you don't have data. You can go also to Asia. This is a temperature-derived, temperature reconstructions derived from tree rings only. And from 1816, you see this from Ed Cook's work, large areas of northern Asia, but also here in the south, India, large parts of India, and southern parts of China were very cold during that year. And interestingly, here it was not only 1860, but also 1817 that were very cold. So there's also an impact on agriculture during those years, 1 year after the Tambora event. Here in these areas, people are depending or were cultivating rice. It was very cold. People were not able anymore, and they switched to opium. And since about 200 years, we know the spread of opium in this area is actually based since about 200 years when people changed due to the cold conditions during 1816, 1817, also related to changes in the hydrological cycle. Then there's a second part about pages 2K is an improvement. So this was work over the last 2 years. So to compile even more proxy information from the different archives. And this is the distribution here. This is the archive type, again, in colors. And here it's also the resolution, what we saw. So we have resolution of sometimes daily or weekly from documentary evidence to tree rings, 1 year resolution, and then you get lower resolved archives that are all over the place here. And we see also an increase of proxies over time, and actually we have here much more. So this is the best what we have, what is published. Of course, people go on collecting and archiving, but that's, I would say, as Edouard mentioned, also state of the art for current high-resolution paléoclimatology. These data are archived, and you can download them for free, and you can use them also for your applications. This is a way of taking everything together. This is a work of Friedrich Ljungqvist and colleagues published in Nature 2 years ago. This is more or less the distribution of the pages 2K network, and then using some statistics to derive 100-year bins of temperature variations here over the last 1200 years. So you see a mean spatial temperature anomaly pattern. This is just qualitative, this is not quantitative, and you see everything that is red refers to warmer conditions, and you can trace that through the centuries. So it's a nice way of using documentary information and other natural archives and to say something in space over longer time periods. Now we come back, work that we did in the frame of a new project, and that's just using high-resolution proxy information. That's the proxies we used. And we can divide them in areas northwestern China, northeastern China, southeast, and the Tibetan area. And the first attempt was just to take the proxies that are in the box or close and use this Bayesian model that assimilates incomplete in space and time proxies to estimate the state of temperature evolution in parts of China over the last 2,000 years. And this is the result for the different regions. So this is the last 1,200 years for southeast China, for the Tibet, northwest and northeast, with associated uncertainties. And as Jan also mentioned, the further you go back in time, the more uncertainties you have, so the wider are these uncertainty bands. And also, Jan mentioned this before 1400, it's quite difficult to say something, and it's actually also in many records here that the further you go back, after 400, 500, 600 years, possibly before 1400, you can reconstruct something, but you have to be aware that uncertainties are large because of the proxy availability and also the resolution. But nevertheless, we were able just to reconstruct on a high temporal resolution for this area. Now there are different reconstructions. We were not the first one. And this is a comparison between our reconstruction, that is new Bayesian statistics that is applied in Europe, in the Arctic, that is considered as a new method that's a good one that performs well, also if you want to reconstruct extremes. So we applied this also to China. So this is an average over all regions in comparison with previous reconstructions. And this is also some kind of a spaghetti plot over the last 1200 years. And these reconstructions are not independent. They share a lot of data about common data. Some reconstructions have additional data. Some have just related to documentary evidence in the southeast. So they share some common predictors, but they are actually not the same. And also statistically, they are derived by different statistical methods. So ours is here the blue one, which is a cool one compared to the other one. And you see quite, in gray here, it's the uncertainties associated to our reconstruction. And what you can see is we have here a bunch of reconstruction that just show rather a mild medieval climate anomaly, then a cooling. So the cooling trend, all of them share the same towards this, if you want to call it, little ice age, so cooler conditions with a maximum in about the 17th century, and then the strong increase in temperature. And here observations show here. So maybe the last decade, the last 2 decades might be really unusual in terms of the last 1200 years, including associated uncertainties. We can also have something in space to see to what extent are the different reconstructions different for specific periods. What we have here, it's the temperature difference for 3 periods. For the MCA, for the medieval climate anomaly, 900 to 1200, minus the little ice age, present minus the medieval period, and present minus the little ice age. And here it's for our Bayesian hierarchical work. This is another reconstruction, and this is from Cook based on tree rings. So it's, again, not independent, but I want to show here it's, for instance, present minus little ice age during summertime. We have more or less all areas today are significantly warmer than during the little ice age. If we go to the present, to the medieval climate anomaly, there seem to be some areas that were warmer, significantly warmer, but nevertheless here in the west, in the east, this might be not the case. There's a lot of red here, present minus little ice age or minus medieval climate anomaly. Nevertheless, there's also changes between our reconstructions and also changes, for instance here, this Xi et al., this points to the fact that maybe in the MCA, in these areas, based on these proxies they have used, it was significantly warmer than today. So this should give you just a way that these reconstructions can be also used in space and can be used to compare periods with periods. This is a plot that shows the difference between, or not the difference, a comparison between the PMIP3, CMIP5 simulations over the last 1200 years, here given in black with the ensembles, and our reconstruction in red. Here we didn't do any detection attribution studies, but here was just the point to what extent are these forced simulations that were presented in the IPCC, how well do they match our reconstruction. So we see there's the red one and the black one, they are not the same, but nevertheless they show some similar features. They show rather warm conditions during the medieval climate anomaly, then the cooling trend towards the little ice age with a minimum around 1600, and then the warming here. So we have to work on this to explain, is this internal variability, is this forced? But it seems to be, at least as a first glance, that the temperature, summer temperature over this specific area of Asia were to some extent externally forced, but also they have some significant internal variability. But this work will go on in the future. And that's just the last figure for this part, where we used at a decadal scale all the proxies to go 2000 years back in time. So this is the last 1200 years that we had a look at, and where it seems the last 10, 20 years seems to be really warm in the context of the last 1200 years. And if we go further back in time, we see the period, the first 200 years that were quite mild, then a cooling trend, cool periods here, and this warming during medieval climate anomaly, Little Ice Age, and the warming today. But still, you see quite a bit of uncertainties you have to be aware of. Now let's change to the second part about the hydroclimate. And this is a much tougher part, as more or less everybody of you are aware, than temperature. So why are dendro or hydroclimatic reconstructions challenging? So generally, we have less reliable instrumental data, precipitation droughts, so they don't go as far back as, for instance, for temperature. So this makes calibration more difficult because we have gaps, we have more uncertainties, we have shorter timescales to calibrate and validate. Proxy records for hydroclimate usually have a lower correlation with instrumental records than temperature proxies, so they have more noise that we have to be aware of, and I will come back to this point. And we actually don't really know, in all cases, what these proxies reflect in terms of hydrological changes. Is it precipitation? Is it soil moisture? Is it water availability? Is it drought? Is it a mixture? So sometimes it's a mixture, sometimes it's clear, but it's tough really to get the signal out of these proxies in terms of hydroclimate. And then also changes in different direction and different location with the same forcing or temperature, so some regions get wetter, some others get drier. And a part I will come back also, that precipitation has a much shorter decorrelation decay length than temperature. So if you are 30, 40, 50, 100 kilometers away of a place, then maybe you don't get a correlation anymore. And I will show this, how this is reflected in the proxy. So that's also here, you might have a strong thunderstorm with a lot of precipitation, and 20 kilometers away it's dry. So it's much tougher. So this means also you need much more proxy if you want to do a reliable spatial reconstruction in terms of hydroclimate variability. I want to show you a couple of examples from Asia we have. Just give you a flair what information we can use for climate reconstruction. So we have to deal with this kind of data or information. This is China. Gerald knows this much better than I do. So this is a qualitative description of rainfall from a Chinese memo from the 10th July 1772. This was done by a governor from Shandong province. So everything that is written here can be interpreted. This is a short text. I give you just half a minute to read what these Chinese information are translated to. So it's very detailed, these memos, and you find a lot of them in different areas and over different periods. So they include information about the hydrological changes, about precipitation at a high temporal and spatial resolution. So it's always for the emperor, and you find them all over the place, and that's just one example. Another example are these dryness-wetness conditions that reflect monsoon season over eastern China back to 1470. So for each year, we have a wetness or dryness index for about 120 of these counties in China. So it was the generation of annals or these memos for local geographic and governmental units expanded greatly in the 15th century. That's why they started at the end of the 15th century. The descriptions of weather conditions, they were relevant to agriculture and living conditions. That's why people wrote a lot about them, and the emperors, they also needed this information. And more than 2,200 local annals and many other historical writings were used to convert this information for specific location in this area here. And for each summer, you will get like an index between very wet, normal condition, so nothing special, or very wet. And you see a compilation over the last 500 years here in terms of normal precipitation, dryness, and wetness, how this changes over time across the 100 sites. So you see, for instance, A are the normal precipitation, so it's
about 40 to 50 sites out of the 100, so about half shows normal condition, then over time they get much down. This means a lot of wetness increased, and the B, these are the dry years, they actually decreased. So you can use a lot of these 100 or 120 information in space and just try to extrapolate in space and get some kind of information about monsoon variability over the last 500 years. This is a very nice compilation of a book of a friend in China, and this here, it's just to give you impression, that's 2 meters. So this is in a book, and you have to fold, you have to make them really huge to see this kind of information. So he compiled all the documentary evidence from what is available over China and draw these maps here. So this here in red are precipitation anomalies over the last 2,000 years. So that's today, that's 2,200 years. That's temperature. So it's qualitative. But all the information, taking into consideration uncertainties, interpreting them. So it's a lot of subjectivity, of course, but nevertheless, it's a nice history of Chinese climate together with information about wars, information about famine, information about grain harvest, and so on. So a nice compilation of what is actually out there. There's also other products. This is the drought atlas of Ed Cooks and colleagues, so using tree ring information and statistically reconstruct PDSI, Palmer Drought Severity Index in space. In the IPCC, we just took this area of India and southeastern China and plotted a drought index over the last 700 years, just to give an information how variable this whole area is. And we have to take into consideration, of course, that sometimes the conditions here in India and here can be completely different. But that's just a spatial average to show that we can plot drought changes over the last 700 or 800 years. Another reconstruction used multi-proxy information for the last 300 years and plotted these spatial anomaly plots. This is a precipitation map for 1816, the year after Tambora, for parts of Asia. So we see areas here that were rather dry, rather wet, here dry. So you can get also the spatial patterns about droughts and wet conditions over the last 200-300 years with multi-proxies. And Frederick Ljungqvist did not only temperature, he applied also his station network towards space to get some kind of general information about centennial precipitation changes over the northern hemisphere, and you see the different centuries from 1800 to the 20th century. Now what I would like to do the last couple of minutes is this new projects we are involved with 2 partners in the UK and in China, just to get a bit more insight in high resolution monsoon variability using expert knowledge, but also documented precipitation proxies over the last 1500 to 2000 years. And this is the distribution of proxies. The different colors refer to different proxies. This is 2000 years ago. This is 850 CE, and that's a network that covers, let's say, the last 15 years. So it's a huge effort to collect all this information because the exchange of publication of proxy data is not in all cases very easy, but nevertheless, I think it's a good network to work with. And I come back to the point about the decay of correlation with space. So we know from today in summer climate or in summer conditions, we can have a thunderstorm here, a lot of precipitation, 50 kilometers away, it's dry. So precipitation is much more variable in time and space. So what we did here, we used the different proxies we have gathered and just checked. We used single proxies and correlated them with the next neighbors across space to see when is a critical distance reached where the correlation is decreasing, that we have no connection anymore between the proxies in the network. So the different colors refer to the green ones, meaning they are cross-dated, high resolution, precisely dated, and then there are red ones with the H model with large uncertainties. So we have high and low resolved, or high and low frequency proxies that we correlate with each other. That's the mean distance, that's the correlation, and we see, independent of the proxies we have, high resolution, low resolution, there's still a significant correlation within about 500-600 kilometers. And then from 500-600 kilometers, it vanishes. So still we can do quite a good job if we don't have every 50 kilometer proxy, but if we have at least a proxy that is in the vicinity of 500 to 600 kilometers in space, then we can do a rather good job. We don't need to have them all distributed, but they have to be in a good place, and they should be within about 500 to 600 kilometers. And something similar is related to the climate signal evidence, that we can show that 500-600 kilometers in space is a distance where you don't have any connection anymore with higher distance. So that's a first analysis just using proxies. And then at the end I want to go to the space. So we have plotted the first principal components between single proxies and all proxies. So this is a principal component that goes about 1,000 years, and this is the first principal component. This shows positive loadings here in the west, negative here, and positive again here. So this means we have this kind of dipole-tripole pattern where we have this associated trend. So if we have green proxies, this is the trend over time. So this means we have, if they are all the same, they are positive. So this means they get wetter over time. The red ones, they refer to drying. So we have this kind of tripole patterns where this area behaves similar, this is similar, but the opposite, and here we have again the same that reflects these trends. And I think that's important to see that the trend in the proxy data suggests a La Nina-dominated medieval climate anomaly and an El Niño-dominated Little Ice Age. And I think from here we can start also to use any other locations to relate the hydrological changes over China with ENSO. With the Arctic we want to do it, and with the other areas, just to try to explain these spatial patterns. And the last point would be, we want to do something again in space. So we talked a lot about proxy information, relevance of proxies, but actually what we would like to do is some kind of a spatial dimension. We want to use the proxies, extrapolate in space. The question is, how many proxies do we need? Where should they be located? What characteristica do they have? What statistical methods? And for this, we can go in a climate model. A climate model in itself is perfect. And here is the distribution of proxies. Here are the contours of the continent. And here what we want to do is just, we have the complete data set within the model over East Asia. These are 366 grid points. And we have the proxy information. There are 38 locations in this case here. And we want to see to what extent can we use these proxies to extrapolate monsoon precipitation in space in other areas where we don't have data. And we can check this. So we can do this kind of pseudo-proxy experiments in the model. We can test there what's the role of the proxies, signal to noise ratio. If we reduce the network a bit, what does it matter? Can we still account for a specific amount of precipitation variability or not? So we have a very nice test bed in the model to check our statistical methods, to compare statistical methods, and also to work with proxy in a model world. And this gives us ideas if we want to go to the real world. Then we know from the model that proxies in this network behave like this, and if we apply the statistical methods, we can actually a good job or a bad job. And this is a first result, that we do a reconstruction of precipitation in the model with our location of the proxies. And as assumed, everything that is red is a positive correlation. So wherever we have proxy locations, in this area we can do quite a good job. If the proxy is reliable and gives us information about past hydrological changes, we can assume that it can reconstruct precipitation quite well. So wherever we have proxies, we can reconstruct. Here we can also test this decay of correlation. When the proxies are too far away, that we cannot actually resolve hydrological changes. So the main point is here, we have good agreement in areas where we have proxies, and we have low skill in areas where we have no proxies. And that's actually a problem. There is even some areas where we can get good reconstructions just by chance. So we don't have data, but nevertheless, by chance or through teleconnection, what Jan explained already this morning, we can really benefit, and we can also reconstruct in areas where we think there's no potential data available. And what we found also, we did some sensitivity analysis in the model world, which methods performs well with this setting of proxy data. And we found that this Bayesian method performs better than a canonical correlation, a multiple regression, or an analog case method. So these pseudo-proxy experiments, they provide important information about signal-to-noise ratio, the proxy type, changing proxy network, method performance, and thus they can really help us also if we go to the step of a reconstruction in the real world. And that's the proxy network we currently have. And based on this, and based on the understanding we have from the pseudo-proxy experiments, we want then to reconstruct monsoon precipitation or droughts or relevant hydrological cycle for parts of Asia. And then we want to combine them with the independent evidence we have from temperature. And of course, we want to understand what changes were actually responsible. Was it volcanic evidence, volcanic eruptions, solar forcing? Was it land use changes, a combination? And when do we see potentially already an influence of human influence on the change of the monsoon variability over the last 100 or 150 years? So the conclusion is, I think what all the presentation showed so far is that we made good progress in paléoclimatology over the past decade through the production of new proxy records, a new compilation on a regional basis, not only referring to temperature but also to hydrological changes, developments of multi-proxy reconstruction methodology. In the past we had one or two methods, now we have a flare and we can test them, what is the best for these specific purposes. And of course we have development of comparison strategies between model experiments and reconstruction to assess the role of external forcing, feedbacks, and internal variability. And we have developed this new East Asian temperature reconstruction, and we found that since 1960 there's a strong temperature increase, and there's also associated impacts like more heat waves, shrinking glaciers in the Tibet and Tian Shan. And we placed these current summer temperature conditions in a historical context by using about 60 proxies, and we used Bayesian hierarchical model to reconstruct temperature in space. And we found a relatively warm first centuries, followed by cooling, and then again warm interval during medieval times, a cool little ice age, but still large uncertainties, and we have actually to work on that. So the work is not done with this, it's just a next step for a better understanding. And we think that the 1990s were among the warmest decades in at least 1200 years. And then if we go to the hydrological changes, the comparison with an ensemble of, the comparison between the ensemble and our reconstruction show rather good agreement, and an important role of internal variability and external forcing. And hydroclimate reconstructions are much more tough, much more challenging, and these pseudo-proxy experiments in the model world can help us to constrain what we can do actually in the real world. With this, I want to thank you very much, and happy if you have questions on any kind of this topic.